So, hello everyone, my name is Shivank Garg. I am from Data Science AI, second year student from IIT Roorkee. And under the course of Applied Linear Algebra, today I will be presenting some applications of linear algebra in real life. So, the format for this video will be first, we will be discussing basic concepts and then their applications. So, let us begin. So first, we will see how a vector is represented. Basically, a vector is an ordered list of numbers. What do we mean by that is first, if you see right here, this is a list of numbers. This is how a vector is represented. It may be represented in other formats also like this. So basically, there are various representations of vectors. So it can be represented like this also. So how is it used in real life? For example, if you have this document right here, and you need to extract the number of times the word in number, horse, and the and document has appeared in it. So what you do is form a vector like this, and then you look to the number of counts of the word here. So basically, once you have looked, you store it here in like this is the number of count in has appeared, and similarly for other elements. So how does this benefit you? For example, this paragraph is only useful to you for these words. You can now omit this paragraph and store it like this if the position isn't really relevant to you. And this is a numerical format. For example, if you are training a ML model or machine learning model, deep learning model, so they basically can't really work on words, so they need numbers to feed in. So this is what you will feed inside the network. So this is how it can be vectors are used. Basically, it also saves a lot of space for you. If you store a document like this, it will take a lot of space. But if you rather store it like this, there is a lot of space saved for you. So now we move to the next application, which is vector addition. So basically, to get the sum, we add corresponding entries of a vector. For example, consider this. This is the first vector. And now we have a second vector, which is 2 comma 3. Now to add the vectors, we can simply add their components. This is the resultant of the two vectors. So how is it useful? We will look to an example of finance. For example, C1 represent the cash flow. So here in the first year, you have a cash flow of positive one, means you have taken a loan of $1 from a bank, but there is an interest rate of 10%. So in the second year, you are required to pay $1.1. But now consider C2, which is this. So here you take a loan from the bank at the second year and have to pay back $1.1 in the third year with 10% interest rate. So basically, if you consider linear combination C1 plus 1.1 C2 and 1.1 right here, because interest rate is 10%. So you get the total 2-period loan with 10% compounded interest. So basically, these type of calculations can be easily done through vectors. For example, if here suppose there was a special bank whose policy was a bit different and this was instead 20% interest. So basically here you would be using minus 1.2 and here 1.2. So this may seem trivial, but for example, if there is a bank for which first it has a 10% interest rate for the first year, then 15%, then 20%. These types of things cannot be directly calculating using mathematics. So these vector addition concepts really help in that types of calculation. Now we will look to inner product. So basically, what is an inner product? Inner product of two vectors is defined as the piecewise elements element piecewise product sum of two vectors. So this is how. For example, this is a vector 1, 2, and we want to calculate its inner product with 2, 3. So the inner product right here will be 1 into 2 plus 2 into 3. So this is how we calculate the inner product of two vectors. So it is the sum of these. So for example, in the application side, if we consider W to be a weight vector, F to be a feature vector, W transpose F is the score. this is something which is really useful in machine learning and deep learning models nowadays. So now if we consider P as the price, Q as the quantity, P transpose Q is the total cost that is spent. For example, if there are two items and price of one is 5 rupees and price of second is 10 rupees, and you buy a quantity 2 of the first item and 3 of the second item. So basically the total cost that you have spent will be 2 into 5 plus 3 into 10. So P transpose Q can be used to calculate the total cost as well. Now, another example in finance is that suppose S gives you the portfolio holdings in shares. Basically, this means that the total holdings in share that you own. So this is the value of the total amount of the shares that you own at present. So P gives the asset price. For example, you hold one share of first company and two shares of the second company, and first one is of 20 rupees and the second one is of 30 rupees. So P transpose S will be 1 into 20 plus 2 into 30, which is equal to 80. This will give you the total value of the shares you have, and this is actually your portfolio holdings. Now we will move forward to the next application. So basically, this is about affine approximation and linear model. So this is how it is done. So basically, for example, you approximate the y to be something beta times x plus v. So this is the approximation of y. This is done under a linear model and you assume the approximation to be linear. So based on the amount and the data, this is used for prediction, and these are affine approximations since these are linear in X, as you can see. So it is called as affine. So basically what this means is, for example, you are given a selling price of a house is $1,000 in some location, and you are given the house area and the number of bedrooms. So basically, you train a model in order to predict. For example, you need to find and predict what is the house area, what is the price of a house for which the house area is suppose 700 square feet and is 6-bedroom house. So you can't really think about anything. So you train a linear model which is done using linear algebra and linear regression to train such model. And in this model, you get a weight vector which is beta and the offset value. So basically when you beta into x plus v, beta x will be the inner product of beta times x and v is the offset value which you add. So basically this will give you the final result of the predicted value. So we can look forward about, we can understand it more through an example. So consider this. Here the house areas are these 0.48, 1.324. These are in square meters. And then these are the number of bedrooms. These are the actual prices and these are the predictions. So as you can see, the prediction may be a bit far apart, but not really. They give you a brief idea of how close, like we can, how they give you a good idea about how the price is going to be. So this is how a linear model is fit. You have these many data points and the model is fit like this. It is a line and the distances from these gives us the difference in the prices, and this is actually what is predicted by the model is here, which is on the line, and these are the actual prices. So based on the data available, you fit a linear model which gives you. So basically the formula for it is, basically, it is done using this. This is the least squares approximation which is used to fit the model. So now we will look forward to the next application, which is about distances. So basically, distance between two vectors is defined in norm form, and it is basically, for example, x minus vector y is the feature distance this. So this will be the, in Euclidean space, we define as it to be the sum of the squares of the differences of all components of the vector. So this is how it is defined. If x is the vector x1, x3 and y is the vector x2, x4. So here, this is how the distance is defined. Now we look to the nearest neighbor approach. What is that? So if these are the vectors, x minus y is the feature distances between the vectors, and z is a list of it, that is the nearest neighbor of it. So basically z is nearest neighbor. If you can see here, the nearest neighbor of x is z3 because it z6, z4, all other z are farther apart from it. So z is the nearest neighbor of x. So basically the distance between x and j is less than all of the other distances between x and others is. So this is the concept. Now we will look towards its application. So for example, we consider here documents dissimilarity. So consider this problem. For example, we have 5 articles: Veteran Day, Memorial Day, Academy Awards, Golden Globe Awards, and Super Bowl. And we construct a dictionary which consists of 4, 4, 2, 3 words. So we calculate the pairwise distances. For example, like in the first example, how we saw, we use the dictionary to find vector representations of them. For example, it is 2, 3, and something like 1 for first vector. Now we normalize this by dividing it by its norm, which is basically root of sum of squares of its elements to make it a unit vector. And then we calculate the distances between these. So what we observe is that we can calculate the similarity of two documents. For example, the lesser this distance, more similar will be the documents. For example, if we see Veteran Day and Memorial Day, they are both holidays in US and they are highly related, we can see. Similarly, Golden Globe Awards and Academy Awards, these are also highly related because the words that appeared there are pretty common. You can see, observe from here. But consider Bowl and Golden Globe Awards, they are not really related. The distances between them is high. So we can use the following approach to calculate the how similar two documents are really are. Now we will look about mean standard deviation. So basically, the average of a vector is the sum of its element divided by n. So one transpose basically represents the one vector. So what is the one vector is, so this is the one vector, the element of all ones. So into this, transpose times x vector divided by n gives us the mean. And the d-mean vector is this. So this vector has mean 0. You can easily observe this. Standard deviation is defined as the RMS of the d-mean vector, and it is x minus mean by root n and sum of all the elements of this. Sum of squared of all the elements, basically the norm of this. And this standard deviation gives the amount xi varies from the average. So how is it used in real life? For example, consider X is the time series of returns on some investment or asset over some period of time. Like we considered earlier, X is a vector, like first element gives you how much you have invested, and then it is represented by the returns. So average of X is the mean over the entire period, and it is usually called the return. For example, your X vector is, so this is your X vector. The average return for this vector will be 3, which is the mean. And this is known as the average return. Standard deviation measures how variable the return is over the period, and it is usually represented as risk in finance. So basically, this tells how much far apart you are from the mean and the return. So this is a typical, if you can intuitively think, this is what early risk represents. And multiple investment with different return time series are often compared in terms of risk and return. Basically, an ideal investment would be one in which the risk is minimum and the return is maximum. So we use a risk return plot to think about the same. So this is the plot. For example, this is the first example. Here, as you can see, the risk is 0 as the standard deviation is 0, and this, what is the return, is really low. So this is an investment. The second investment is right here. Here first return is high, second the return is low. Basically this BK, AK, these are the average returns. So when we average these out, we get the overall average return, which is the return of the investment. So here we get a negative and then positive. So this is the second investment. This is the return plot for the third investment. And here it goes down always and then goes up really fast. So this is a highly variable. So here the risk is really high. So what you want to choose, a B or C investment would be an ideal choice if we consider, as the risk here are pretty low, like not really high, and the returns are very high. So these both are ideal investment. This may not be a very ideal investment because the return is not very high, and this is a really bad investment. So the linear algebra concepts can help us determine the various returns and how, like, where should we really invest our money. So this is a very good application of it in real life. So this is known as a Chebyshev's inequality. So basically, xi minus average of xi is greater than equal to alpha times standard deviation of x. This The number of entries, fraction of entries for which this occurs is no more than 1 by alpha square. This is what is stated by Chebyshev's inequality. And we will look to its application. For example, if the mean is 8%, standard deviation is 3%, the losses which can occur, losses being basically the loss in the investment, is this. So basically, for less than 14.1% of the period, we have incur losses. So this can really help us to determine which type of investment should we focus on. If the loss is very high, like if we are having losses for high periods of time, you probably wouldn't consider that investment to be very good. Now, angle between two vectors, it is defined as the cos inverse of A transpose B divided by the normal vector A into normal vector B. And this is a number in 0 comma pi, the range of 0 comma pi. Basically, it is an acute number that satisfies A transpose B is equal to norm A into norm E into cos of this angle. So its application, it is highly used in spherical distances. For So basically, sorry for the disturbance here, we will be continuing. So this is how spherical distances can be measured using these angles. For example, there is a point on Earth which is at point A and another point is there at point B. For example, you need to calculate the distance between India and USA. So you can't really dug a tunnel through the Earth and go to B. This is what the normal approach would look like if we subtract the vectors. Basically, we want the distance on this sphere. So to calculate it, we take the radius, which is this, into this angle right here. It gives us the distance along this track rather than digging a tunnel, which is a much more better approximation of the distance between 2 points. So now we consider document similarity problem again by using angles. So lesser the angle between two objects, the more similar they are. So if we consider Memorial Day and Veterans Day here, we can see the distance, the angle between them is pretty less because they are pretty similar vectors. They may be like this. This is first vector and this is second one. They are similar. Similarly, Golden Globe Awards and Academy Awards are also similar vectors. But if we consider these Golden Globe Awards along with Memorial Day, these are very different in each other because if we intuitively think they are not very similar, what similarity is there between Golden Globe Awards and Memorial Day? So we can see that they are very far apart in terms of angles also. So this gives us an intuition of document similarity if we don't really have an idea about it. So now we will move to the next topic, which is clustering. So basically, our goal in clustering is to divide or partition into k groups, and we want the vectors in the same group to be close to one another. For example, we partition this into these three groups. It is done using the k-means clustering algorithm, in which we consider the distances of each point from the mean in the cluster and form these clusters. So basically, what is its application of this concept? For example, there is a dataset known as the MNIST dataset. So it is a handwritten digit recognition dataset, and we form 20 clusters of it. So we see that it has like clustered into different types. So basically it is a handwritten digits data set from 0 to 9. We can see 0, 1, 2, 3, and similarly the four right here, 5, 6, 7, 8, and 9. All the digits have been clustered according to them, and these type of digits which you can see are not really clear. These can be either a 7 or 9. Such types of digits are placed in one cluster, and similarly these type of blurry or noisy images are placed in another cluster. So this is a very important technique. For example, it can be used in real life also. If we consider a college and we need to classify the clusters into various groups, we form a cluster, first cluster of say electrical students, second of EC students, third of data science students, and fourth of CSE students. So this type of approach is highly used in real life also. So now we will look to the Gram-Smith orthogonalization process. So basically, if we have n vectors like this, we orthogonalize them by subtracting each of these. This is an iterative process, and this is also a test for linear dependence. If any of these turn out to be zero, we say that the this vector is linearly dependent on the other vector, so it is used there. As finally we normalize them, and it has a lot of other applications also. Now let us look to some applications. So this is the intuition behind it. For example, this is the vector a1, this is the vector a2. So q1 tilde is right here, and q1 is here, q2 tilde is here. So when we q1 tilde is basically a1 in direction of a1 only, but normalized. So this circle represents all the vectors of norm 1. Basically, this is a unit circle in higher dimension. So here, if we subtract minus q1 transpose a2 q1 from a2, we get q2 tilde and normalize it. So basically, this is a set of orthogonal vectors. So this is used to form orthogonal bases. Now, what is its application? We will look to it. In quantum mechanics, it is used to form orthonormal bases for Hilbert spaces. So these are useful in describing quantum states. In computational theory, it is useful in many transformations. And in signal processes, it is used to create orthonormal signals from the initial ones. And this is used to reduce the noise. Basically, if we infer two signals, for example, if we add these two signals, these are two signals. On adding them, there is a lot of noise right there. So basically, in order to reduce them, we orthogonalize these so that the distances, basically the noise on addition of these is pretty less. And it is also used in robotics for pathfinding and many such more applications. Now we will look to relation. Basically, a relation is a pair of objects labeled 1 to n, such as 1, comma 2, 1, comma 3, 2, comma 1, 2, comma 4. This right here is a relation. So it is similar to a directed graph like this. 1 and 2 are connected to each other, then 1 and 3 are connected, then 2 and 1 are connected to each other, then 2 and 4 are connected, similarly like this. So it can be represented as an adjacency matrix. This matrix right here is called an adjacency matrix. Now, if we use it in graphs, we call it as incidence matrix. Also, in this, Aij is 1 if edge j points to node I. For example, this right here, this 1 points to 2. So basically 1, 2. This is plus 1, but 1 points to 2. So 2, 1 right here is minus 1. Similarly, for this edge 2, comma 3, 2 is pointed to 3. So basically this is positive, and similarly there is a negative of this also. So this is how we form the incidence matrix. So what are its application? Basically, one of its applications is in circuit solving, which is a pretty common one. So basically, if we need to conserve the flow of currents through it, we form such type of an adjacency matrix, and we name the currents to be plus 1 if this is entering current, minus 1 if it is a leaving current, and we multiply it with the current, this current vector, in order to get the solution. So this really is how KVL equation, the Kirchhoff's equation, is derived. So we will now look at some more applications of it. So now flow conservation, basically, M vector gives X flow of something along the edges. Basically, the something which is flowing along the edges can be represented in such a representation. So the flow can be of heat, money, power, mass, electric current, like we discussed, as well as people. So there are many such applications. Xj means the flow follows edge direction. Basically, the flow is from here to here. So this is positive Xj. And if this is the type of flow, it is negative Xj. And this vector right here gives the net total flows. So if we add all the flows right here, so if this is a circuit and we are adding all the flows, so we get the net total current in the loop. So this AX is a n vector that gives us the total or net flows. So AXI is the net flow in node I. For example, here we multiply AX and we look at this third component, we get the flow in the third node. And AX equal to 0 is known as flow conservation and X is called the circulation. So basically in linear algebra, what we call X as is the null space of the matrix A. And this type of, and this equation right here has a lot of real life application. Now we will look at some of these applications. Now, first application is potential and Dirichlet energy. So suppose V is an n vector called the potential and Vi is the potential value at the ith node. So U equal to A transpose V is a vector of potential difference across the edges. So basically, if here the potential is V2, here the potential is V1. So when we subtract and when we multiply A transpose V, we subtract V2 minus V1, the first element, if we consider this as the first edge in A U equal to A transpose V will be the potential difference across this edge. So basically the Dirichlet energy is the square of these. Basically, so it is the like similar to how the potential energy is defined, which is the sum of potential difference. In electrical engineering, we define it like this: the sum of the potential differences across all the nodes. So this is how it is the formal definition. And when the potential energy is small, the potential across are similar basically as the sum of square addition is similar and small. So now how we form a system of linear equation, basically this is a system of m equations in n variables. These x1, x2, x3, these are n variables and these are m equations. So aij are the coefficients, and if we write it as a11, a12 and so on into amn into x vector is equal to b vector. So this is basically a linear system of equation and b is called the right hand side. So this type of equation can be easily written in this compact form of ax equal to b. Now these are some of its applications: economic equilibrium analysis, electrical circuit solving, which we had looked at earlier, network flow control, and balancing chemical equation. Now we will look at these applications in detail. Balancing chemical equation, basically, if this is a chemical equation, A1 R1 plus dot 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 AP RP gives B1 P1 plus these are the various product elements. So basically, these are positive coefficients. From using conservation of mass, we get R minus P into AB equal to 0. This is a compact vector matrix representation of the following above form, and AB, which is the null space of this matrix, gives us basically the solution to this, which is the balanced chemical equation. So this is how it is very helpful in the field of chemistry, because if you are balancing a reaction with high number of reactants and products, doing it by hand or by standard methods which are usually used and taught to us is like really tedious, but this calculation of null space can be easily done on computer or by hand too. So this is how it is very useful and systematic. And now if we are using charge balance, it is similar to how we discussed the previous balancing. For example, here, if we are considering two elements of chromium, two elements of oxygen and minus two charge right here, and then A2, A1, this is to be fine, and Fe2 plus is here, we have its plus 2 charge, and H plus is here. Similarly, these are the products formed. So R minus P into A equal to 0. So if we calculate this using the null space calculation, we get A1, A2, A3, B1, B2, B3, which is the balanced chemical reaction. Now we will look at a homogeneous economy. In general, a homogeneous economy is one in which sources and industries are completely interdependent. For example, here, something is produced by one industry is completely used by the other two. These, for example, the coal industry supplements the electric and steel industry and vice versa. So this is what we are considering. And in general, most economies are homogeneous when we study them. So here, for example, for the coal economy, the distribution of output, there is zero output of coal economy in purchase by coal. So this is PC, and then minus 0.4 of it is there because it is being purchased and this is being produced. And for steel, minus 0.6 this. And for, if we consider the electric economy, electric industry, they are purchasing 0.6 amounts of coal, and then they are actually producing 0.9 PE because 0.1 of it is used by them and minus 2 PS. So this basically, solving this linear equation is similar to calculating the null space of a matrix. And this type of calculation helps us to calculate how much ratio and the price of the, how, like, what type of ratio is there between the purchase and output from the various industries. Now, flow networks. Now, if we consider flow networks, consider this network right here. Here in the, it is a traffic flow network. For example, here, the flow coming in at a port is equal to 400, 300 plus 500, and it is equal to flow out this. And similarly, this. So basically, we can form a 5 cross 5 matrix system to solve this, and calculating AX equal to B. This is not really a null space problem, but rather AX equal to B calculation problem, which gives us the X vector, which is the actual flows here. So calculating this by hand is also very difficult, and this is a practical application. For example, consider the aeroplane problems. For there is a port, say not really a port, but an airport in Mumbai, and two aeroplanes are coming on it from south, two from east. How much many should go from west, and from how many should go from west and south? So basically, this type of calculation can be used in real life. Now, in conclusion, before ending this, linear algebra is a fundamental branch of mathematics that deal with vector space and linear mappings between them. So it is used in a lot of fields, from economics, computer engineering, physics, to solve very complex problems. It is also used in image processing, like if we want to reconstruct images, we can use that also, and in data compression, machine learning. So these linear, earlier these types of things had to be done on hand brute force. So linear algebra has really helped in this field, and it has enhanced the quality of how problems are solved, and it has a lot of real applications in life. So I hope this presentation would have been useful to you, and I hope it was a good one to learn new things. Thank you.